going to discuss as you know, the chapter number 12 is continuing algebraic expression. So today's our topic will be using algebraic expression formulas and the rules. So we have seen earlier also that the formulas and the rules in the mathematics can be written in a concise and general form using the algebraic expression. We see below several examples. Parameter and the formulas. The parameter of an equilateral triangle is equals to 3 into the length of its sides. If we denote the length of the sides of a equilateral triangle by L, then the parameter of the equilateral triangle will be 3L. Similarly, the parameter of the square is 4L, where L is equals to the length of the side of the square. Now parameter of the regular pentagon is equals to 5L. So L is the length of the side of the pentagon and so on. So area's formula, as we know, like if we denote the length of the square L, and then the area would be with the formula L square. If we denote the length of the rectangle by L and the breadth by B, then the area will be L into B, that is LB. Similarly, if B stands for the base and H for the height of the triangle, then the area of the triangle is B into H over 2, that is BH over 2. Once a formula, that is algebraic expression for a given quantity, is known, the value of the quantity can be computed as required. For example, for a square of a length 3 cm, the parameter obtained by putting the value L is equals to 3. The expansion of the parameter of the square, that is 4L. So that means 4 into 3 is equals to 12 cm. Similarly, if we have to find the area of the square is obtained by putting the value in the L is equals to 3 in the expansion for the areas of the square, that is L square, then the result will be 3 square, means 9 cm square. Now rule for the number pattern. If a natural number is denoted by n, then the successor is n plus 1. If we check this for any natural number, for example, if n is equals to 10, its successor is n plus 1, that is 11, which is known. Now likewise, then we have, if a natural number is denoted by n, 2n is the even natural number and 2n plus 1 is an odd number. So let us check it for any number, say 15. 2n is equals to 2 into n is equals to 2 into 15 is equals to 30 is indeed an even number. So 2n plus 1 equals to 2 into 15 plus 1, that is 30 plus 1. 31 is indeed an odd number. Okay, if you look at this pattern, we can see here 4 square shape having the 4 sides or the 4 line segments we can see here. Now this is a combination of 2 squares, but 7 line segments are required. This is a combination of 3 squares, but 10 line segments are required. Combination of 4 square, only 13 are required, and so on. So if we consider this pattern, this shape, then we can see here 3 line segments, here 5, here 7, here 9. Now moving ahead, if we see here, make the similar pattern by the basic formulas. Okay, as you can see, this is looking at P, then how many in the line segments are there, 5 are there, then this is, we are making P with P, then how many are there, this is 9, then H 5 likewise. So now some more number patterns. Now when we talk about the some number pattern, now we see some more number patterns. So look at the another pattern of the number, this time without any drawing to help us. 3, 6, 9, 12, 3 and all. If you see here, these are the dot patterns, these are the number 3, 6, 9, 12, 3 and the numbers are such that they are multiple of 3 arranged in an increasing order beginning with 3. The term which occurs at the nth position is given by the expression 3n. You can easily find the term which occurs in the 10th position, which is 3 into 10, that is 30, and the 100th position will be 3 into 100, that is 300, and so on. Pattern and geometry. What is the number of diagonals we can draw on one vertex of a quadrilateral? So looking here, so like here we are drawing 1, then from the 1 point only, from in the pentagon we can draw 2, hexagon 3. So it means the number of diagonals can be drawn on the one vertex of a polygon of n side is n minus 3, like 4 minus 3 1, 5 minus 3 2, 6 minus 3 3. Now on the basis of this, now we'll discuss the exercise, discuss and solve the exercise 12.4. Looking at the first question is observe the pattern of the digits made from the line segments of equal length. If you find such as segments, digits on the display of an electronic watches or the calculators. Yes, so we can see here, so it is given like 6, 11, 16, 21, so on, 4 7 11 13, sorry 4 7 11 10 13 3n plus 1, then 7 12 17 22 5n plus 2. So if you look here, so the question is if the number of digits found in the, is taken to be n, then the number of segments required to form the digits is given by the algebraic expression appearing on the right of each pattern. How many segments are required to form 5, 10, 100 digits of the kind? So first we look here. If here the first one is symbol is here 6. Now number of digits used are 5 here. Okay, then in the second one it is 10, then 100. Likewise they are saying, so for this number of digits, so 5n plus 1, so number of segments will be 26. Then 5n plus number of segments will be 51. 100, 5n plus 1, 5 into 100, 500 plus 1, 501. Then for the second part, digits required are 5 here. Then now the question is to form the 5, 10 and 100. So if you look here, formula is 3n plus 1, so just putting the values here. In place of n we are putting 5, so 3 into 5 15, 15 plus 6 16, then 10 into 3 30, 30 plus 1 31, then 100 into 3 plus 1 301. Then for the third part, number of digits number are 5, 10, 100. For 5, formula is 5n plus 2. To put 5 into n, that is 5 into 5 25 plus 2 27, then we have 10 into 50 50 plus 2 50 200 into 5 500 500 plus 2 502. So in this way, now moving towards the next question of, you see here, so these are answers of the first 26 51 501 16 31 301 27 52 502. Now in the question number 2, what we have to do now, they are saying using the given algebraic expression to complete the table number system. So it is given like first is 2n minus 1. First will be n, as we put n is equals to 1, so 2 into 1 2 minus 1 1, then we put 2, then 4 minus 1 3, then we put 3, then 10 minus then 6 minus 1 5, and likewise. So we have to fill all these dotted. So putting, if we see here putting n is equals to 100, so n is equals to 100 means 200 100 minus 1, that is 199. In the second it is 3n plus 2, so putting n is equals to 5, so 3 into 5 plus 2, so we have here 17. Then putting n is equals to 10, 3 into 10 plus 2, that is 32. Then n equals to 100, 3 into 100 plus 2, that is 300 plus 2 302. Then third is 4n plus 1, so 4n plus 1 means here putting n equals to 5, n equals to 10, n is equals to 100, so we have 4 into 5 plus 1, that is 21, 4 into 10 plus 1, that is 41, 4 into 100 plus 1, that is 401. So in this way, then moving towards the next part, so we can see here it is given like 7n plus 20, so n is equals to 5, so 7 into 5 plus 20, answer 55. Then 7 into 10 plus 20, that is 90, then 7 into 100 plus 20, that is 720. Then we are putting n square is equals to 1 as a formula, putting n is equals to 5, so we have here 5 into 5 plus 1 26, then n equals to 10, 10 into 10 plus 1, that is 101. Then n is equals to 100, 100 into 100 plus 1, that is 101. Sorry, not 101, but it is 10,001. Then if you have to write in the table form, as we can see, so all these values we have taken out, we have to just put here like 199, 17, 32, 302, 21, 41, 401, then 9, 20, 55, likewise. Okay, so with this we come to the end of the exercise as well as the end of the chapter. So thank you very much.